Good afternoon, everyone, and welcome to the 2CC webinar series. Today we have Dr. Xianglin K. from Michigan State University in the Department of Physics and Astronomy. Dr. K today is going to be talking about thermal Hall effect and insulating van der Waals magnets. He is also a 2CC user in bulk crystal growth. Please go ahead, Dr. K.
Okay, thank you very much for the introduction. And first of all, I would like to thank you for the invitation to give this seminar in 2DCC. Yeah, as you just mentioned, actually, yeah, I submitted a proposal to 2DCC. It was accepted, but turns out that we never went there for the experiment, which was unfortunate. But yeah, so the postdoc from Xianglin student have been working very hard preparing the samples for us. So really appreciate that. And good afternoon, everyone, for both online and also in person at Penn State. Yeah, good to see you. And so, as just mentioned, today I would like to talk about some of our recent results on the thermal Hall effect in insulating van der Waals magnet. So when we talk about van der Waals material, I guess the first material that usually will come to our mind is the graphene, right? So thanks to the weak van der Waals force between the layers, one can very easily exfoliate the graphite into the monolayer graphene just using the Scotch tape, right? So for such a single layer graphene, it has been found that the system will show some very interesting or exhaustive electronic properties, which are associated with the direct electronic bands, such as the quantum Hall effect. And this phenomenon was discovered by these two gentlemen who shared physics Nobel Prize in 2010. So the discovery of the graphene really opens up a new research field for studying the 2D van der Waals material beyond graphene. So one of the prominent class of the materials are van der Waals magnets. So with the magnetism acting as a control knob, 2D van der Waals materials will provide a fertile playground for the discovery or exploration of the novel physics phenomena, as well as the potential new physics. So the table I'm showing you here just lists some of the 2D van der Waals material or 2D van der Waals magnet that have been studied in the previous several years. So from this table, we can see that some of the materials or majority of the materials are chalcogenized or halide and so on, right? And from this table, we could also see that some of the materials could be ferromagnetic and some of them could be antiferromagnetic or even multiphoric. And some of the materials could even be the candidate of so-called quantum spin liquid, type spin liquid, such as the ruthenium trichloride, which has been a very, very hot material that has been studied in the past 4 or 5 years ago. Okay, and from the electronic viewpoint, the material could be metallic, or it could be semiconducting, or could be even insulating. So in addition to the various magnetic ground state and potential unconventional magnetism in van der Waals magnets, the materials could also show very interesting or exhaustive properties. So for instance, ferromagnetism could even persist down to the real 2D limit, okay, or just a monolayer, right? And also depending on the layer numbers, the exfoliated 2D van der Waals magnet could show different magnetic properties. It could be ferromagnetic or it could be antiferromagnetic. And one could also tune the magnetic ground state properties using the non-thermal perturbations, such as strain electric gating, as well as the proximity effect. And furthermore, new phenomena, such as the so-called molar magnetism, can emerge by just staking different type of van der Waals material, or even the same type of van der Waals material on the top of each other and with different twisting angles. Last but not the least, van der Waals magnet could also find a lot of potential technology applications, particularly in the spintronics field. Therefore, van der Waals material represents a great platform for both fundamental scientific research as well as the practical technology applications. So today, I would like to focus on another aspect of van der Waals magnet. That's their topological properties. So we know that one of the major breakthroughs in condensed matter physics and material science community in the past 2 decades is the discovery of the topological insulators. For the topological insulators, they are insulating in bulk, but on the edge or on the surface, they could be metallic. And such an exhaustive electronic properties are protected by the electronic band topology. So the discovery of the topological insulators opened up again a new field to search for the new topological states of quantum matter, such as the direct semi-metal, wave semi-metal, and so on. So as a matter of fact, topology was a mass concept. So the very famous example is the continuous deformation of a coffee cup into a donut. So during such a deformation process, there's one quantity which remains unchanged. That's the size, the number of the hole in this case. So this quantity is so-called topological invariant. In condensed matter, a topological invariant is a number that does not change under the smooth deformation of the Hamiltonian, such as the chain number, which is the integration of the Berry curvature of the electronic bands over the first Brillouin zone. Well, it turns out that the concept of topology can be nicely applied to describe the magnetic excitation of the materials. So for instance, let's say that we have a ferromagnetic Kagome system with the spins pointing up. Then these excited spins, which are represented by red spins, will be completely decoupled from the red spins or from the black spins. Okay, just due to the Kagome geometry. As a result, they would have 3 bands, magnon bands. 2 of them are dispersive and 1 of them is flat. And these 2 dispersive magnon bands will cross each other at a K point. Okay, but we know that again for the Kagome systems, the invergent symmetry is broken relatively at the center of the nearest neighbor band. In this case, the Yalovsky-Maria interaction, also called DM interaction, is allowed. So if we take into account the DM interaction in a Hamiltonian, then we can see that these 2 dispersive magnon bands would open a gap at this direct point or K point. Okay, and by calculating the Berry curvature of as well as the chain number of this gap magnon bands, it has been shown that this gap magnon bands will be topological. So topological magnetic excitations has been observed in a few real systems, and one of them is copper-13 BDC. The left figure I'm showing you here is the inelastic neutron scattering results. If you could see it clearly, if you could see from the picture, we can see that there's a gap opening between the top band and the bottom band. Okay, and the right figure is the simulated results using a linear spin wave theory by taking into account the DM interaction. And from the simulation results, we can clearly see that again there's a gap opening at this K point. So the agreement, the nice agreement between the simulation and the experimental results suggests that the system shows topological magnetic excitation. So if you have a system showing topological magnetic excitations, then you could have the chiral edge magnons, chiral edge magnon modes. Okay, and theory has shown that in the presence of the longitudinal thermal gradient, this chiral edge magnon modes is going to give rise to thermal Hall effect. And the thermal Hall conductivity will be determined by the Berry curvature of the magnon bands, as we can see from this equation here. Okay. So just a few more words about the Hall effect. So we all know electric Hall effect very well. So for the electric Hall effect, we applied a longitudinal electric current, right? And then in the presence of the perpendicular magnetic field, we will expect to see a transverse voltage drop. And this is going to give us electric Hall effect. Similarly, for the thermal Hall effect, here we apply a longitudinal thermal gradient along the sample. Then in the presence of the perpendicular magnetic field, along the transfer direction, we could also see a thermal gradient as well. And this is going to give us thermal Hall effect. So thermal Hall effect has been observed in metallic systems or in insulating compounds. For the metallic systems, the dominating heat carrier could be the charge carriers, either electrons or holes. And for the insulating compound, the heat carrier could be the magnons or phonons. So as I just mentioned, thermal Hall effect has been observed in the electrical systems. So for instance, here I'm showing you an example that we just studied last year. So here we can see that we have been trying to do a lot of transverse transport measurements on a metallic Kagome system, so-called terbium magnet 166, which is again another interesting system that has been studied in the past 2 to 3 years. So for this system, we have observed very large thermal Hall effect, as you can see from the left figure here. And from the right figure, we can see that in this system, we also found very large anomalous electric Hall effect as well as the lens effect. So from all these three transport, transverse transport measurements, we can conclude that the system shows the topological electronic properties. Recently, the thermal Hall effect has also been observed in some insulating compounds, particularly in the past 2 to 3 years. So the thermal Hall, for instance, the thermal Hall effect has been observed in the garnet compounds, in the cupellate compounds, or even in the ferromagnetic and dielectrical compound, the strontium titanate. Okay, and for these systems, phonons has been argued to be the dominating heat carriers for the observed thermal Hall effect, although the underlying mechanism remains unknown or debated for most of these cases. And so far, the magnon thermal Hall effect has only been observed in a few magnetic systems, including the 3D particle compound, lutetium vanadium 227 systems, as well as the quasi-2D Kagome systems, copper 13BDC compound that I just showed you in one of the early slides. So if we look at the thermal Hall effect of these two systems, particularly if we just look at the scale of the thermal Hall conductivity, we can see that the thermal Hall conductivity is quite small. Okay, it's only in the order of 10 to the minus 3 or 10 to the minus 4 watt per meter per Kelvin. Okay, so the signal is very small. And about 5 years ago, there was an inelastic neutron scattering study on another system, so-called chromium triiodide. And chromium triiodide is a honeycomb ferromagnet. The inelastic neutron scattering data is shown on the figure on the right. And from this figure, we can see that there's a gap opening between the lower magnon band and upper magnon band. Okay, and again, since this system has a honeycomb lattice full of chromium atoms, therefore the second nearest neighbor DM interaction is allowed. So if the DM interaction is included in the Hamiltonian by doing the simulation, then the authors found that the simulated results would agree very nicely with the experimental results. And this gap opening could be accounted for just by including the DM interaction. Therefore, they suggest that this chromium triiodide system, in principle, should also possess topological magnon or topological magnetic excitation. And this motivated the study that I'm going to show you for the rest of my talk. So the material of our interest is vanadium triiodide. This system has a similar crystal structure to chromium triiodide. It also has the hexagonal structure. And an earlier magnetic stability and heat capacity measurements found that this system has a structure phase transition at about 76 Kelvin, followed by a ferromagnetic phase transition at about 50 Kelvin. And the earlier study shows that the EG axis is along the C direction. Recent single crystal neutron diffraction experiments found that actually the EG axis is slightly tilted away from the C axis. And furthermore, from the neutron diffraction experiment as well as the synchrotron X-ray diffraction experiments, it has found that below the structural phase transition, this honeycomb lattice is normal perfect. Instead, there will be a small distortion on the honeycomb lattice. So these two photos shows the images of the chromium triiodide single crystals that we grow using the chemical vapor transport in our lab downstairs. And from our magnetic stability measurements, we can see that, again, the system shows a ferromagnetic phase transition at about 50 Kelvin, and it has a large EG axis component, which are all very similar to what has been reported in the literature. So now we talk about the thermal transport measurements. So here we carry out the thermal transport using so-called one heater and three sensor technique. So these three sensors are labeled as T1, T2, and T3 here. So such a setup allows us to measure both longitudinal thermal conductivity as well as the transverse thermal conductivity simultaneously. Now let's take a look at the longitudinal thermal conductivity first. Figure on the right shows the temperature dependence of the longitudinal thermal conductivity measured at zero field, which is the blue curve, as well as the 7 Tesla, shown by this red curve. If we take a look at the zero field data first, immediately we can see that they are two anomalies corresponding to the structure phase transition and the magnetic phase transition. Okay, so this is nothing surprise, right? However, very interestingly, with a 7 Tesla, we see the thermal Hall conductivity is even larger than the thermal conductivity measured at zero field. So this comes as a surprise to us at the beginning. So as I mentioned earlier, right? So this is compound. It's an insulating compound. So for an insulating compound, there are two dominating heat carriers. One is the magnon, and the other one is the phonon. So if magnon and phonon behave independently to each other, then we would expect that the magnetic field is going to suppress the magnon population because the magnetic field is going to push up the magnon bands to a higher energy. In this case, the magnon population is going to reduce. Then, in principle, it's give us smaller thermal conductivity. This is the object of what we observe here. So again, in reality, we observe an enhancement in the thermal conductivity in the presence of magnetic field. So actually, this tells us that in the system, it shows a strong magnon-phonon coupling. Why? Because the magnon will be scattered by the phonon will be scattered by the magnon. Therefore, it's going to reduce the thermal conductivity at zero magnetic field. Now, if we apply a magnetic field, as I just mentioned earlier, the magnetic field is going to reduce the magnon population. This is going to reduce the phonon scattering by the magnons, and this is going to restore the phonon thermal conductivity contribution to the total thermal conductivity. Right? That's the reason that we see an enhancement in the thermal conductivity in the presence of magnetic field. So again, the take-home message here is that the system vanadium triiodide shows a strong magnon-phonon coupling, and this is important in a few slides that I'm going to show you later on. Okay, now let's take a look at the transverse thermal Hall signal. So the figure on the right shows the thermal Hall conductivity as a function of magnetic field measured at several temperatures. And immediately we can see very interesting features, at least two. One is that the thermal Hall conductivity is quite large. It's in the order of 0.01 watt per meter per Kelvin. So this is the magnitude of the thermal conductivity we observe here is at least 1 to 2 orders of magnitude larger than the magnon thermal Hall conductivity that I show you in one of the early slides. And the second interesting feature is that even in the presence of in the absence of the magnetic field, we can see that the thermal Hall conductivity is still quite large. It's almost the same as the thermal Hall conductivity we observe at 0.5 Tesla. So this tells us that the thermal Hall effect that we are observing here, it's an anomalous effect, right? Because it does not really require magnetic field. So we carry out the thermal Hall measurements at a bunch of the temperatures from low temperature all the way up to the temperature, which is very close to the transition temperature of the system. And again, we see a very nice thermal Hall signal over a wide range of temperature. And from the previous slide, then we can extract the temperature dependence of the anomalous thermal Hall conductivity, as I'm showing you here, okay? And we repeat the measurements on a series of many different samples. And the figure I'm showing you here, just showing you the longitudinal thermal conductivity as well as the transverse thermal Hall conductivity for 3 different samples. We can see that all the features are very similar across different samples. So this tells us that indeed we are seeing some intrinsic effect of this system. So then we would like to ask, what's the mechanism of the thermal Hall effect that we are observing in these vanadium triiodide systems? Is it purely driven by the phonons? The answer is no. And the reason is because, again, the thermal Hall effect that we are observing here is anomalous. Okay, even without applying the magnetic field, we still see a very large thermal Hall conductivity. But if the thermal Hall effect was driven by the phonons, then it requires the magnetic field. Without a magnetic field, your thermal Hall signal is going to be zero. Therefore, this is cool that the thermal Hall effect that we observe here is purely due to the phonon. The next question is, could it be due to the internal magnetic field of the magnetization? Because again, vanadium triiodide is a ferromagnetic, right? So internal, you are going to have a large internal magnetic field. So the answer to this question is no, either. And the reason is because just by comparing the magnetization as well as the thermal Hall effect measure a high magnetic field, you can see that the magnetization saturates a high magnetic field. But on the other hand, the thermal Hall conductivity decreases when we go to the high magnetic field instead of being saturated. So immediately this tells us that the thermal Hall effect that we observe here should be something related to the dynamic property of the system. That's the magnons, instead of related to the static magnetization of the system. So to further understand the physics of the thermal Hall effect that we observe here, via the collaboration with the theorist, we examine the corresponding 2D Hesper speed model based on the honeycomb lattice. So the Hamiltonian is written in the formula here. So here we include the 3 exchange interaction as well as the DM interaction, anisotropy interaction, as well as the GM interaction. Okay, so let's look at the magnon band structure first. If we do not take into account the DM interaction in the simulation, okay, we can see that the upper magnon bands and the lower magnon bands will cross each other. The upper magnon bands is represented by this kind of yellow curve, and the lower magnon bands is represented by the blue curve. Again, we can see that without DM interaction, these 2 magnon bands will cross each other. On the other hand, if we take into account the DM interaction in the Hamiltonian, then immediately we can see that the upper magnon bands will separate from the lower magnon bands, and there will be a gap opening at a K point. And around this K point, you will have a very large Bailey curvature, as we can see from here. And again, due to this large Bailey curvature at a gap opening points, it will give rise to a large thermal Hall conductivity, as we can see from this figure, or as we can see from this equation here, right? The figure on the bottom right just shows the comparison between the calculated results and the experimental results. The experimental results is the red dots, the calculated result is the blue curve. And we can see that a high temperature, the calculated result, agreed nicely with the experimental result. So this suggests that a high temperature, the thermal Hall effect could be dominated by the topological magnons due to the DM interaction. But in the meantime, we see that at a low temperature, there's a large discrepancy between the experimental data and the theoretical results. So what's the reason for that? Now, if we try to plot the difference between the experimental result and the calculated result, and plot it as a function of temperature, and this is what we got, as shown by these blue dots here. So here we can see there are 2 peaks. We can ignore the peak at high temperature, and this is because this peak at high temperature is an artificial effect. Because the thermal Hall conductivity was calculated based on the mean field theory, which could not accurately capture the fluctuation phenomena near the phase transition temperature. Therefore, we could just discard this one, but focus on the low temperature peak. Okay. In the same figure, we also overplot the temperature dependence of the longitudinal thermal conductivity, like I showed you in one of the earlier slides. And we can see that these 2 curves maximize almost at the same temperature, right? So immediately this tells us that the thermal Hall effect that we observe at low temperature is something related to the phonon. But how does the phonon play a role here? One of the possibilities is through the magnon-phonon coupling or magnon-phonon hybridization. So our theory collaborator performed another calculation by including the magnon-phonon coupling in the Hamiltonian. So for simplicity, only the outer plane phonon mode of the vanadium atoms are included in the calculation. So the top 2 figures shows the magnon and phonon modes, or magnon and phonon bands of the calculation, and the bottom two figures shows the projected Bethe curvature of the magnon and phonon modes. Okay, and the left two figures are the calculation results without taking into account the magnon-phonon coupling, and the right two figures for the calculation with the magnon-phonon coupling included. And immediately we can see that if we include the magnon-phonon coupling, okay, in the calculation, you can see that the magnon and phonon modes will hybridize together and intercross with each other. Okay, so by the way, the red color represents the magnon bands, and the blue color represents the phonon bands. So we can see that at this intercrossing points, again, magnon and phonon hybridize. Okay, and interesting, we can see that at this intercrossing point, it gives rise to a very large Bethe curvature, as I show you here in figure D here. And we can see that the Bethe curvature due to this magnon-phonon hybridization is even larger than the Bethe curvature due to the DM interaction, right? As we can see again from this figure D here. And since this magnon-phonon hybridization occurs at low temperature, therefore it's going to contribute to the thermal Hall conductivity at low temperature. And indeed, this is exactly what we see here. The green curve shows the calculated thermal Hall conductivity by taking into account the magnon-phonon hybridization, and then you can see that at low temperature, indeed, the we do see the thermal Hall conductivity. Okay, even though that there is still some discrepancy between the experimental data and the new calculated results, but such a discrepancy might be due to just a very simple toy model that we use in the calculation. Okay, again, we did not consider other phonon modes, or we did not consider other potential mechanism that will contribute to the thermal Hall effect, such as the side jump effect of the phonons, side jump scheduling of the phonons, and so on. Okay, so the figure on the right shows the anomalous thermal Hall angle, which is defined as the ratio of the thermal Hall conductivity to the thermal conductivity as a function of temperature, right? And basically, we could separate this curve into two regions. For the high temperature regions, the thermal Hall effect is dominated by the topological magnons, while at the low temperature, the thermal Hall effect is dominated by the magnon-polarons due to this magnon-phonon coupling. Okay, so now the story I'm telling you here is on vanadium triiodide. And as I mentioned, vanadium triiodide has a similar crystal structure as well as the magnetism to the chromium triiodide. So you might wonder what happened to chromium triiodide, right? Because chromium triiodide, because as I mentioned earlier, so previously someone did an inelastic neutron scheduling and saw the magnon gap opening, right? And suggested that the system might show topological magnetizations. So this is the motivation for our study. So what happened to chromium triiodide? Now let's take a look again. Just to remind you, the inelastic neutron scattering study on this system. So there are two inelastic neutron scattering studies on this system from the same group. From the earlier study, we already see this figure in the previous slide. From this earlier study, they conclude that the DM interaction is 0.31 MeV, which is going to account for the large magnon gap opening here in this system. By the way, in the earlier study, the magnon gap value is about 4.6 MeV. Therefore, it requires a large DM interaction. Okay, 0.31 MeV. About 3 years later, they published another paper on the same journal, and they did some more extensive study, and they also recognized the samples and so on. But anyway, this is the results. And from the new results, we can see that the magnon gap is much smaller. Right now, it's about 2.8 MeV instead of 5.6 MeV in the previous results. And then based on this new results, they could extract the DM interaction, which is about 0.09 MeV. Okay, and then you might wonder, well, on the same system, how come the DM interaction is different or the magnon gap is different? And the reason is because the system, this magnon gap opening could have some kind of extrinsic contribution coming from the sample mosaic. In the earlier study, as I showed you earlier, right, all the samples were grown using the so-called CVT method. And as we know, using the CVT method, the sample that people could grow usually is very small. Okay, very, very small and very, very thin. Therefore, for inelastic neutron scattering studies, we need to coordinate many, many pieces of the samples together. Okay, so for the earlier study, okay, by this group here, the sample mosaic is about 70 degrees. And in a more recent study, the sample mosaic is about 8 degrees. Therefore, they conclude that there's some kind of extrinsic contribution from the sample mosaic to the magnon gap opening in this system. Okay. But anyway, even with this 0.09 MeV DM interaction, as I'm going to show you later on, we will still expect to see the magnon-thermal Hall effect. So the question is, do we really see it or not? Okay, so to pursue this study, we grew the chromium triiodide single crystals by ourselves. Again, this photo just shows the single crystal growing using a CVT in our lab. And from the magnetic susceptibility measurements, we can see that the system orders ferromagnetic below 61 Kelvin. And from the thermoconductivity measurements, we can see that the system shows much larger thermal conductivity compared to the vanadium triiodide system. And interestingly, just from the raw data, we can see that around the magnetic phase transition temperature, we barely see any anomaly corresponding to the magnetic phase transition, right? Again, this is a feature different from the vanadium triiodide. However, if we apply the 3 Tesla magnetic field and we do the measurements on the thermal conductivity, we can see that there is a slight enhancement in thermal conductivity in the presence of the magnetic field. And we could see this feature more clearly if we plot the difference between the difference of the thermal conductivity between the 3 Tesla and 0 Tesla data. And this is shown in this yellow curve here. Here now we can see there's an anomaly in the magnetic phase transition temperature. And then at low temperature, the thermal conductivity increases in the presence of the magnetic field. Now let's take a look at the thermal Hall signal. So the left figure shows the thermal Hall resistivity as a function of magnetic field that we measure at about 24 Kelvin. Okay, the blue dots, the red dots. The black dashed curve is the MH curve. And from this data, we can see that the system shows a very nice thermal Hall signal in chromium triiodide at this temperature, right? We also carry out the measurements with different heating power. Okay, as you can see from the right figure here, you can see all these 3 data overlap very nicely, which tells us that indeed the thermal Hall signal that we observe here is an intrinsic feature. Okay, so we perform the measurements, the thermal Hall measurements of this system at a series of temperatures, and then again from this slide or from these results, we can extract the temperature dependence of the anomalous thermal Hall conductivity. Okay, and this is what we got. And here I'm showing you the graph for 2 different samples, and we can see that basically the features behave very similar. Okay, from this figure, immediately there are 2 features that we can see, right? The first one is, well, okay, both samples show very large thermal Hall effect at low temperature. If we plot this thermal Hall effect together with the longitudinal thermal conductivity of the chromium triiodide, and we can see that again the thermal Hall signal and the thermal conductivity will maximize almost at the same temperature. So immediately this tells us that the thermal Hall effect that we observe in this chromium triiodide at low temperature is something related to the phonon, and highly possible again is related to the magnon-phonon coupling. Right? So this is one feature that we notice. A second feature that we notice is that in contrast to the vanadium triiodide, for chromium triiodide, at high temperature, we can see that the thermal Hall conductivity just decreases very quickly. At high temperature, basically, we see a very small thermal Hall signal, or thermal Hall signal is just complete emission at high temperature. Okay, but previously, I told you that the most recent inelastic neutron scattering study on chromium triiodide suggests that the DM interaction of this system should be about 0.09 MeV. So as I mentioned, with 0.09 MeV, one would still expect to see a large enough thermal Hall effect. And this is confirmed by the DM interaction done by my collaborator. So in the graph here, it shows the thermal Hall conductivity as a function of temperature calculated with different DM interaction values. For 0.09 MeV DM interaction, which is shown by this green curve, you can see that the calculated thermal Hall conductivity will be about 10 milliwatt per Kelvin per meter, which is about 1 order larger than we observed in our experiment. Okay. As a matter of fact, based on our experimental values, we think that the upper threshold value of the DM interaction in this system, if it exists, would be about 0.01 MeV only. So again, the DM interaction in this system might be very small. Okay, might be much smaller than what has been claimed from the inelastic neutron scattering experiments. So again, what could be the potential reasons for the small or missing thermal Hall conductivity in these chromium triiodides? As I just mentioned earlier, the recent inelastic neutron scattering said that, well, okay, they could have some extrinsic contribution from the sample mosaic to the magnon gap opening that has been observed in inelastic neutron scattering experiment. In the most recent inelastic neutron scattering study, the sample mosaic is still 80 degrees. Therefore, it's likely that this 8-degree sample mosaic still dominates the magnon gap opening observed in the neutron scattering data. And as a matter of fact, the group did a simulation, okay, just by taking into account the DM interaction, taking into account the sample mosaic, but without DM interaction, as shown by this middle figure here. And you can see that indeed the simulated results is going to give you a gap opening here. Okay, so again, it's likely that the magnon gap observed in the inelastic neutron scattering experiments might coming from the residual sample mosaic 8 degree in the most recent study. Okay. And as a matter of fact, this sample mosaic is really important in understanding the magnon gap opening in systems. So for example, here's another system, which is the chromium tribromide, okay, a system compound of chromium triiodide. So the figures C and D plot here was a recent study by a group a couple of years ago. And in this study, we can see that there also exists a large magnon gap. And again, the authors of this paper claim that this system also shows topological magnons. But actually, 1 year later, last year, there was a study who did some simulation and found out that even without taking into account the DM interaction, but just by considering the sample mosaic, one would observe a very large magnon gap in the magnetic excitation. Therefore, such a magnon gap opening might not be intrinsic, might not any indication of the topological magnons. And the most direct evidence coming from an experimental study, which was reported last year as well. So this is an experimental study by a group in PSI in Europe. So they did another inelastic neutron scattering study, but on a single piece of chromium triiodide single crystals. So the earlier study shown here was done on core-9 samples. Okay, and the figure on the right, or the most recent inelastic neutron scattering study was done on a single piece of single crystals, single crystals. And then from the experimental study, they found that, well, when you analyze the data, if you just integrate a very small K region, okay, which means that if you do not consider the sample mosaic, then in reality, you will not see any magnon gap opening. But on the other hand, when you analyze the data by integrating a large K region, in other words, by taking into account the sample mosaic, then you are going to see a large magnon gap opening. Okay, so this directly tells us that, again, sample mosaic is very important. Okay, sometimes it could just fool us. Okay, sample mosaic could give rise to the magnon gap opening. And similar conclusion also applies to another chromium system. This time is a chromium trichloride system. done by a group in Oak Ridge National Lab. And again, this study was done on a single piece chromium trichloride single crystal. And again, there's no magnon gap opening in this system. Instead, it's going to form so-called direct magnons. But if you consider the sample mosaic, then we are going to see the magnon opening again, magnon gap opening again. And again, all this tells us that where in reality, in this chromium based honeycomb systems, maybe the DME interaction could be very small. Okay. Another potential reason they might account for the missing thermal Hall signal in this system comes from a recent theoretical study. So in this recent theoretical study, they found out that if we combine the effect of the interlayer interaction with JC, as well as the third neighbor intralayer interaction, then in some regions, we can see that the magnon gap will be zero or will be gapless. The magnetic excitation will show gapless feature. As a result, the thermal Hall conductivity could be close to zero or could be very small. So again, there are two potential reasons. One is either the DME interaction is very small, or maybe there's some kind of combined effect from the interlayer coupling and the third intralayer coupling in this system. Okay, so here's the summary of my presentation. So both vanadium triiodide and chromium triiodide are 2D van der Waals ferromagnets with honeycomb magnetic lattice, and both of them show enormous thermal Hall effect. For vanadium triiodide, it shows a dual nature of the thermal Hall effect. A high temperature is dominated by the topological magnons, and a low temperature is dominated by the topological magnons due to the magnon-phonon hybridization. And for chromium triiodide, we only observe the thermal Hall effect associated with the magnon-phonon hybridization. A high temperature, the topological magnon feature is missing. And this might be due to, a high temperature, the thermal Hall effect signal is very small. And this might be due to a small DME interaction in the systems, or due to the combined effect of the interlayer coupling and for the neighbor intralayer coupling. So to really resolve this issue, in this neutron scattering study on a single piece chromium triiodide would be very important and very helpful. So before I end, I would like to just quickly show you one of our recent study, thermal transport study on iron dichloride, FeCl2. Okay, this system apparently is also a van der Waals magnet, where the iron atoms will form a triangle lattice instead of a honeycomb lattice. And the system orders antiferromagnetically below 23 Kelvin. And within the layer plane, it's ferromagnetic. Between the layers, it's antiferromagnetic along the C direction. And the system shows a very small critical field. We could change it, we could flip the spins to ferromagnetic alignment just by applying 1.5 Tesla. And from our thermal transport measurements, we can see that the system shows a very, very large magnetization thermal conductivity, almost 600%. And from our thermal Hall effect study, we can see that the system shows a very large thermal Hall effect. Okay, and the thermal Hall effect will even change the sign. Okay, by using the magnetic field, by switching the material from antiferromagnetic to ferromagnetic. Okay, and this is our recent study on this is our recent paper on this system. Okay, and we think that one of the reasons for the thermal Hall signal that we observe here might be associated with the magnon-phonon coupling in this compound. And this is a very early neutron scattering study on this system, which was published almost 4 decades ago. Okay, so yeah, this is what I'm going to tell you. And I would like to thank my collaborators, my students in AMSU, and my theory collaborators in University of Washington. Okay, and funding agency for the DOE and NSF. Thank you very much for your attention.